All right, everyone. Today we are going to determine the pressure drop in a pipe, and we're going to do it twice. Once for when the pipe is horizontal, once for when it's vertical. We have water at 60 degrees Fahrenheit. It's flowing steadily in a 2-inch diameter pipe, horizontal this time, and it's made of smooth plastic. You can generally assume plastic is smooth at a rate of 0.2 feet cubed per second. We want to determine the pressure drop over a 200-foot long section of pipe. Okay. So that's what we've got. Horizontal pipe, 0 L. We're going to want the properties of water at 60 degrees Fahrenheit. If you're not given them, you'll need to look them up. At 60 degrees, water is going to have a density of 62.36 pound mass per feet cubed and a viscosity of 7.536 times 10 to the negative 4 pound mass feet per second. Beautiful. We also know that our flow rate Q is 0.2 feet cubed per second, and that L is 200 feet. We know that we will be working towards this equation, delta P equals 2 rho F L over D U squared. I want to point at this absolute value for a second. We talk about the pressure drop, and of course in class we said that pressure always goes down as you go along the pipe. It's a drop. So that delta P is actually always going to be negative, but it is much more common when we say the pressure drop is however much to be talking about the absolute value. And of course in this equation, it has to be the absolute value because F is always, the friction factor is always positive, just like with the friction factor in your physics class of yore. Okay, so what do we know? We know rho, L, and D. We don't know F. We'll get to it. And we can figure out U. U is going to be Q over the cross-sectional area is going to be Q over pi D squared over 4 is going to be 0.2 feet cubed per second over pi times 2 over 12 feet, because we're in inches and we want to get that into feet, which is the unit we're using for everything else, over 4, and we get 9.17 feet per second. Okay, that's our velocity in our pipe. From there, we can get the Reynolds number, which we'll need to get our friction factor. Reynolds number in this case is, well, in all the cases, always and forever. It's rho UD over mu. By the way, once in my job interview for my internship that I had when I was y'all's age, the interviewer asked me what the formula for Reynolds number was. I think that sort of question it's basically a way to check whether you have been paying attention in your classes at all. So you need to remember the things I'm telling you, is my point. You never know when it will come up. All right, so we get a Reynolds number of, well, of 126,431.9, which can be approximated with the significant figures we have as 126,400. Either way, it's definitely turbulent, all kinds of turbulent. So we use one of the relationships for friction factor for turbulent flow in order to avoid having to solve an implicit equation right now. We will use an explicit version. F is equal to 3.6 log of the Reynolds number over 6.9 raised to negative 2, which in this case will come out to 0.00425. That's our friction factor. Okay, so we go back to the equation we set our eye on from the beginning. Delta P is equal to 2 rho F L over D U squared is equal to 2 times 62.36 pound mass per feet cubed times 0.00425 times 200 over 2 divided by 12, not bothering to write the units there because they're both in feet, so we'll cancel out, times 9.17 feet per second squared. But I am not going to stop there. This result will give me something with pound masses in it, which is not a normal unit of pressure that anyone uses. So I want to make sure to convert using this conversion, which you should remember from your previous classes in this major. 1 pound force is equal to 32.2 pound mass feet per second squared. And we will end up with 1658 pound force per feet squared, which is still not a very normal unit of measure. So we will convert it into pound force per inches squared, or 11.5 psi. That's our delta P. All right, back here. Let me see. U should be the same because Q is the same and D is the same. The Reynolds number will be the same because rho, U, D, and mu are all the same. F will be the same because Reynolds number is the same. But go ahead and check. I told you we would also do it vertically. So here we are. So this is exactly the same setup, except for now the pipe is vertical. Boom. Okay, it's vertical, so height 1 is we'll just set it at 0. And then height 2 will be at 200 feet. Why 200 feet? Because we're going over a 200-foot long section of pipe. We've set it vertical. Makes sense. So we have all the same values as before, except for now we also have a delta H of 200 feet. All right. So this time, since it's vertical, we have a change in the dynamic pressure is equal to 2 rho F L over D U squared. And have any of these values changed from the last time we did this? No, they have not. Just right. So we're going to have a change in the dynamic pressure of 11.5 psi, just like before. But we want the pressure drop, not the dynamic pressure drop. And we know that the absolute value of the dynamic pressure is equal to the absolute value of delta P plus rho GH. Actually, you know what? Let's go this way. We know that the change in the dynamic pressure is equal to the change in the pressure plus rho G delta H negative put them to this side. We know negative delta P is equal to negative, boom, or in other words, right, because both of those deltas are going to be negative. So if you have the negatives of a negative, you get positives or the absolute values of those pressure drops. Okay, so delta P, which is what we were looking for, is going to be 11.5 psi plus 62.36 pound mass feet cubed times 32.2 feet per second squared times 200 feet. And we want to get this into units of psi. So that will be times 1 pound force per 32.2 pound mass feet per second squared times 1 over 144. That'll be feet squared per inches squared, like so. And we will end up with 98.1 psi. And notice that the contribution from gravity is actually quite big. Anyway, so there we have it. We have done it once horizontally and once vertically. Woo, good for us.